Okay, in this video I would just want to reinforce the lecture that I did on failure theories for static failures, which is chapter 5 of our textbook, and specifically right now we're talking about ductile materials, not brittle materials. And we have 3 failure theories that we will look at for that situation. They're listed in the textbook together as the maximum shear stress theory, section 5-4, the distortion energy, or the von Mises theory, section 5.5. And both of these presume that our yield stresses, our yield strengths, are the same for both tension and compression. If we are both ductile and we have different yield and compressive tension and compressive yield stresses, then we have the ductile Coulomb theory, section 5-6. Okay, next time we'll take a look at brittle materials. I'm just talking about ductile for today, excuse me. So, the first one, maximum shear stress theory, we've been talking about all semester long, and of course it comes from the Mohr circle, and I'm simply going to point out that we have a very simple set of equations to use to test the maximum shear stress theory, and it has to do with values of sigma A and sigma B. Let me remind you precisely what those are. This is for a plane stress situation where we have a stress square with sigma x's, sigma y's, and tau xy's on it. That plane stress situation can be used to draw a single Mohr circle where the far right end of that circle is called sigma A and the far left of that circle is called sigma B. And that right now we're not looking at the three-dimensional circle. These cases take into account the three total circles for us. So if we just follow the rules here, we will reach the right answer. And so, if we have a state of stress, possibly given by a sigma x, a sigma y, and a tau xy, we must first do Mohr circle and turn it into a sigma A and a sigma B. Let's take a look at that. I think I've got it right here. So here is our Mohr circle where we plot normal stresses on the horizontal axis, shear stresses on the vertical axis, and it shows you where all the equations come from for Mohr circle. But I'll simply point out that right here, okay, equation 3-13, we have a sigma 1 and a sigma 2, or we could call this sigma A and sigma B, is the average of the xy stresses plus the radius of the circle, square root of the radius of the circle involving sigma x, sigma y, and the tau xy pieces. So this will give us our sigma A and sigma B, where sigma A is always the furthest to the right, sigma B is always furthest to the left in this notation. So if sigma A and sigma B are both positive, and sigma A is larger than sigma B, then in this case both points are on the right hand side of the circle, which means we do have to consider the full 3D circle. Okay, so wherever the origin is, maybe the origin is right here, then we've got a larger 3D circle that we have to deal with for finding the maximum shear stress. Okay, so this equation amounts to making sure that our sigma A does not become bigger than the yield stress. Case 2 has A bigger than B as always, but A is bigger than 0, B is negative. So A is positive, B is negative. This circle crosses the 0 axis, therefore this is the largest of the three circles, and therefore the difference between sigma A and sigma B is the diameter of the circle. Okay, and the diameter of the circle is going to be compared to the yield stress to make sure that we don't fail. Finally, case 3 says neither A and B are bigger than 0. They're both negative. A is still further to the right than B, so B is the leftmost point, and we want to make sure that sigma B does not become less than the negative yield stress, or that the absolute value of sigma B doesn't become bigger than the absolute value of the yield stress. These are the 3 cases for maximum shear stress theory for plane stress. And now the key thing is, if we have sigma A's and B's, we are ready to go. If we don't have sigma A's and B's, we first have to go to Mohr circle and use the Mohr circle equation to get our sigma A's and our sigma B's. That's everything there is for the maximum shear stress theory. Now moving down to the distortion energy theory, or the von Mises theory. Again, we talked about derivation last time. We didn't entirely derive it, but we did come up finally with an equation that could be plotted and compare it to the maximum shear stress theory. And we see the dotted line is maximum shear stress, the solid line is the distortion energy theory, and they're very similar. Matter of fact, they match exactly at several key points, but the maximum shear stress theory is a little bit more conservative. And so here are the key equations for calculating maximum shear stress, the distortion energy values. I mean, it all boils down to blending the state of stress down to one number. Okay, that one number denoted sigma prime, sometimes called the von Mises stress. And if we have our full 3D principal stresses, we've done Mohr circle to the max, so we have sigma 1s, 2s, and 3s, this equation will give us our von Mises stress. We won't have that terribly often in this class. Okay, if instead we have our full triaxial state of stress with sigma x, sigma y, sigma z, and all 3 taus, that would be the most complicated cube that we could have, then we can calculate the von Mises stress from this equation, plugging in all 6 numbers. What's more likely to happen is we have a state of plane stress, and in that case this equation would simplify because all of the sigma z's would go to 0 and all of the taus that involve the z's would go to 0, and we're left with a simplified form of the equation right here. And this is the one we'll probably end up using the most, where we have our sigma x's, sigma y's, and our tau xy. Let's take a look at, well, no, let's move on to our final theory, which is the Coulomb theory, which says we have material properties in which we have a compressive yield over here different than yield and tension, probably, and this one certainly is negative, but it's probably going to be a larger number than this number. And if we draw the 2 circles, a circle for tensile yield and 0, a circle for compressive yield and 0, and we fit tangent lines to those 2 circles, these tangent lines become our bounds on our largest Mohr circle that would be said to succeed. And so here we have this gray circle might represent our state of stress, that being the largest Mohr circle for our state of stress that is just barely fitting within these bounds. If we were to look at the equation that flows from that by looking at the triangles that are illustrated right here, if we straddle, if our Mohr circle, our largest one, straddles the 0 boundary, then the equation that defines its characteristic is right here. It involves a sigma 1, a sigma 3, so we have to have those principal stresses, and that is our biggest circle, and our yield strength and tension, and our yield strength and compression. It turns out we have 3 options for this theory as well, and we want to look a little bit carefully at this one. Okay, for plane stress, when we have 2 non-zero principal stresses, A and B, so this is a plane stress case, if they are both positive, okay, then this amounts to basically a maximum shear stress theory, okay, sigma A greater than sigma tension. If they're both negative, this is almost maximum shear stress theory, except we're using the larger circle that comes from the compressive yield stress, sigma B must exceeding negative compressive yield strength would cause failure. If we're straddling, sigma A is positive, sigma B is positive, negative, we're straddling the 0 axis, then we use the governing equation that come from the 2 tangent lines. So this is also a very simple theory. Let's take a quick look at example problems. Won't look at all of it, we'll just look at a little bit of it and see how it's presented. This is example 5.1 in the notes. It says we know the yield strength in tension and compression both to be 100 kpsi. That means we only have 2 theories to choose from. We have a true strain and fracture of 0.55. That tells us that it's ductile. So we want to estimate the factor of safety for the following principal stresses. So we've got to know what kind of stresses are these. These are principal stresses. And in this case we have sigma A, sigma B, and 0. So our stress element would look like a square that has 70 on both sides and no shear stress. Okay, and so these two numbers being the same, we would go to a case 1. Well, let's see. First of all, we're going to use two different methods. We're going to use maximum shear stress, and we're going to use the von Mises or distortion energy theory. Let's see. It says estimate factors of safety. It didn't say what methods to use, but that is what's going to happen. Okay, so for that first one, sigma A is 70, sigma B is 70, sigma 3 is 0, so it does fit the plane stress case. We can plug this into the von Mises equation, and we get a 70. Interesting. And we get a factor of safety of 100 over 70 of 1.43. For the maximum shear stress theory, sigma A and sigma B are both positive. Sigma A is positive 70, sigma B is positive 70. They're both bigger than 0. So in this case, we want to make sure that sigma A, which is 70, does not exceed the 100. And so our factor of safety again would be the 100 over the 70, and we get a 1.433 again. Let's take a quick look at Y. Okay, notice our failure lines for the maximum shear stress theory. Notice the failure ellipse for the von Mises theory, and notice that we were on a situation where sigma A and sigma B were both equal. And if they're both equal, we're on this 45-degree line, and on the 45-degree line, both theories give exactly the same answer. They both reach the boundary at the same place, so we should expect them to give the same answer. Okay, let's just look carefully at the others that we have. We have a 70 and a 30. They're both positive, and a 0, so the 70 should rule for the maximum shear stress theory. Okay, the 100 over 70. But for the von Mises theory, we're going to have a mixture of 70s and 30s, which gives a von Mises stress of 60.8, slightly a little bit lower than the 70, okay, giving a slightly larger factor of safety of 1.64. Therefore, as we've said before, the maximum shear stress theory is more conservative than the distortion energy theory or the von Mises theory. Okay, we're not going to work the rest of these. You can take a look at them. In this case, though, we do have a positive and negative, so that these would straddle the 0 boundary. So that would be the middle case. We have them both negative, and this would be the third case. All three of them being 30 is very interesting, and I'll leave it to you to take a look at what that factor of safety comes out to be. It's kind of surprising if you don't think about it. Okay, and so you're going to see this kind of a problem for homework where first of all they claim they're giving you sigma A's and sigma B's. Then you're also going to see problems where they give you sigma X's, sigma Y's, and tau's. What you have to do in that homework is take the sigma X, Y's, and tau's, process them through Mohr circle, the Mohr circle equation, or graphical Mohr circle if that's what you're after. Process them through Mohr circle to get the principal stresses, and then go back to the failure theory, or solve them just like this problem once you have the sigma A's and the sigma B's, which would be either use the distortion energy equations. Scrolling too much. Equation 512 says I have all three principal stresses. Equation 514 says I have a full 6 state of sigma X, Y, Z's, and tau's. Or equation 515, which says I have plane stress state and I have the sigma X's, Y's, and tau's for plane stress. For maximum shear stress, I have the 3 cases. That should be everything you need to do the homework for this Friday. Okay, thanks.